In part 4 of this series, making a Arduino powered brake light, reverse light, underglow light thing for my 350Z, I mentioned the fact that we changed from using a separate Arduino Nano and HM10 Bluetooth module to using an ESP32 chip, which has Bluetooth integrated into it. And the fact that we needed to therefore change a bunch of the code that we'd created over the first 2 parts of this series in order to accommodate that new chipset. I didn't want to delve into the code in that episode of the series because it would have bloated it to too long. So we've done it as a separate one now, and I'm going to step you through one bit at a time how I went from changing the code for the, like I say, the independent Nano and HM10 Bluetooth to an ESP32. So if you do want to work with using Bluetooth connections in a simpler ESP32 chip, this is going to show you how to do that. This video is actually going to accomplish 2 main things. The first one is we're going to go through the code that we wrote before and look at how we can improve it for production standards with things like making sure we're using dry programming standards, DRY, don't repeat yourself, and actually removing of unnecessary third-party libraries that we use that maybe aren't needed if we do things a slightly better way, and just making the program more functional and more reusable. It's just making the code better. Secondly, we're going to look at the differences between how we communicate between the Arduino on a HM10 Bluetooth and how we communicate using an ESP32, because the setups between the 2 standards are quite different. I guess I should stop blabbing about it and get on with the code. So to catch up from where we left off, this is our light setup code. I'm just going to do a 30-second blast through of this just to remind everybody what the code does and where we're at. So we've got our includes, stuff for the Bluetooth, stuff for the lights, stuff for the memory, stuff for splitting strings. We've got our pin definitions, some setups for the LED definitions, our basic state management. Then we set up our objects for the Bluetooth and the lights. We've got some stuff here to do with extracting memory values and then storing them in red, green, blue formats. We've got the default setup for the Bluetooth string, which is being sent by our mobile application. We've got definitions of our pin modes, inputs and outputs. We've got serial monitoring setup, Bluetooth setup, NeoPixel light setup, and then all this, which basically just goes and says, are the numbers in memory valid? And if so, set them. Then we've got the reading of our various buttons. If the Bluetooth's on, then we're doing the settings. Then we've got our basic state manager, which looks at what button is being pressed at any one point in time and then changes things, but does it so that the lights only change when changes actually happen rather than pinging off requests all the time. Then we've got our set settings, which is when the mobile application is talking to the Arduino. It does one of 2 things. So it sends in a string, and that string is either the word ready, which then tells the Arduino to send back the current memory values of the colors stored in there so that the mobile can set it as a default state. If it's not that, it's a string of comma-separated colors, which we used string splitter for to basically find the various color indexes and then set them back into memory. Then we had a bright red for brake, a white for reversing, a glow mode, which sets the color based on the brightness with an adjustment here for the brightness, and set the normal DRL mode, which is a dim red. A lot of this can be simplified and made much, much better. So we're going to start by looking at some of the areas we can reduce repetition and just make the code a lot better. The easiest payoff we're going to get is these 4 functions at the bottom: set brake, set reverse, set glow, set DRL, because they all do relatively the same thing. They set the NeoPixel lights based on a color value and a brightness value, but what we've done in here is actually define what those color and brightness values are in each subfunction. There's kind of really no need to do that when we could do it all with one function. So let's create a new function here, which we'll call set NeoPixel color. And that is going to take 4 variables: int red, int green, you can probably tell where this is going, int blue, and int brightness. Then what we can do in here is just reuse this code. So what this code is doing, just to remind you, is looping through the pixels one at a time based on the number of pixels we have, and set the color based on that. In this one, it's actually setting it to max brightness, so that's 255. So it's setting this to bright red, 25500, so RGB. So instead of this, we're just going to put in red, green, and blue, which means we can then pass those values in whenever we're calling this function. But what about brightness? Well, NeoPixel actually has a thing set up. If you want to change the brightness of the whole strip in one go, you can just do neopixel.setBrightness and then give that a value between 0 and 255. But we're just going to pass in brightness. And then NeoPixel Show sends all of those updated colors, stored brightnesses, all that kind of stuff. It sends it all to the strip and sets it. So that's a new set NeoPixel color function, which takes these 4 variables. So instead of having all of that, we can get rid of everything there. And where we've called these 4 functions, instead we're going to do set NeoPixel color, and then B, this is all going to change in a minute, but B, so breaking, is 25500 with a brightness of max brightness. If you remember, we have 2 brightness values, so max brightness and normal brightness. So we'll just refer to those by those constant values. So now break does set the NeoPixel color to red, 00, max brightness. Then reverse can be white, which is 255, 255, 255 with normal brightness. So in the previous thing, we did a mathematical function where we calculated a reduced brightness value. We don't need to do that anymore because we can just pass it the full color and then just set the adjusted brightness by using the set brightness attribute on the NeoPixel lights. Set glow we'll come back to in a second. Set DRL is full red but normal brightness, which again will do the adjustment. And then set glow is going to be the normal brightness, but the R, G, and B values are dynamic. We have these memory R, memory G, memory B, which are set as global values, and so they're the things that are staved in memory. So we're going to set these for now, spoiler alert, to memory red, memory green, memory blue. Just because I'm a little bit anal about this stuff, I just want to make the spacing here a little bit more aesthetic. There we go. So that has got rid of those 4 big functions and replaced it just with that simple bit of code and 1 function. Immediately makes things better. But what we can now do is actually change this current state, save state, state manager switch thing. Because at the moment, the way the state manager works isn't really ideal. We can't refer to things changing outside of the state management. If we wanted to like set a mode based on another factor, we'd have to integrate it into the state management. So there are better ways of doing that. Also, using these as bytes here isn't efficient in the form of memory, and it isn't efficient in the form of readability. So B, R, G, like what happens if I've got 15 different modes? It's going to become a little bit arduous in order to remember which one is which. So we're going to redefine these, how these variables and the current state management stuff is done, and we're going to extrapolate out this function. Let's go to the top and look at where we do the state management here. So at the moment we've just got a guide for what they are, but they're not actually defined or set anywhere. Let's just change that to something that makes a bit more sense. So we'll define a few different modes. So we're going to define DRL mode, and that's like the default one. So we'll do that as 0. And we're going to define these as integers, so we can just refer to them as integers throughout the entire code, even though we're going to use this worded term. They're actually integers that are getting passed around. It'll make sense in a minute. So define break mode. So break mode is going to be 1. Define reverse mode, which is 2. And finally, define glow mode, which is 3. So even though these are integers, I can refer to it as reverse mode. And so when I'm in the code later on, I can just read reverse mode, and it makes a lot more sense. So these current states and save states need to change to the current state is going to start as break mode, and the save state is going to start as DRL mode. Again, it gets rid of that little hack that we had in there where we had to put a space in because it was a byte, even though it didn't exist as a byte. So these obviously aren't bytes anymore, they're integers. So like I said, they're defined as integers, even though we refer to them as the word. So this is how our state management looks now. So when we come down to where we actually use the state manager, when we're doing these, the current state is going to change to break mode. Reverse is going to be reverse mode. And glow mode. And DRL mode. So this is good. This is now a lot more readable. Then this bit, where we're actually using those states, we're going to take this out and create a new function. We'll just pop it here for now, which is void display mode. And that's going to take a value, an integer value of mode. And then if we put this code back in here, we can switch based on mode, which has been passed in. And if it is break mode, do this. Reverse mode, you see where this is going. Glow mode. Let's add an extra one. DRL mode, and the DRL mode should be the same as that. Now the default here isn't really going to ever get called or used because there's never going to do a display mode that doesn't have the value passed into it, but it's a catch just in case. So we've now got this display mode, and what we're going to do if the current state is not equal to the saved state, then display mode of the current mode or current state. What I should really do here is change all the terminology from current state to current mode. It'll just keep things a little bit more consistent. So current mode, and then saved mode. Because these are modes and the buttons have states. So saved mode, saved mode. Now it has modes instead of states, and the buttons have states. So they're on or off. This so far is good. We have massively reduced the amount of code in there, and we've massively increased the readability of it. Something that we do a few times is this. So this is checking whether or not each one of these values is between a certain range, 0 to 255. And we do it here, and we also do it when we do the load state at the top. So it makes sense, again, to create one function that will do that for us. So what we're going to do is create, let's just throw it at the top here as a helper function. So we'll call it void is valid color. And that's going to receive an integer value of a color. All I want this function to do is return true or false, because that's what we're doing when we're putting all those if statements in. We're saying, is this thing true? Is this thing true? Yes, no, and then adds them all together. So we're simply going to return color is greater than or equal to 0 and color is less than or equal to 255. That's it. So it's going to say, does the value of the color that is passed in satisfy these conditions? If it's outside of that, it will return false. If it's inside of that, it will return true. So here, where we've got these memory stores, what we can just do is memory 0 is valid color memory 0. And again here is valid color mem1 and is valid color mem2. Not only is it more readable, it's easier to understand what is going on here and why we're doing it. So instead of just seeing all those random numbers, you're now saying, oh, okay, I'm validating, is this thing a valid color? And we can also reuse that down here. So this is using the cent_r. So just for the sake of it, take this mem 1, 2, and 3. So this is using cent_r, cent_g, and cent_b. Lovely. If we wanted to go one step even further than this, what we could do is say void is valid color each, and then pass that int red, int green, and int blue, and then return is valid color each red and is valid color each green and is valid color each blue. So what this would mean, again, maybe not necessary here, but what this will now do is basically allow us just to pass the RGB to is valid color once, and then this will validate whether or not all three of those individually, hence each, is a valid value. So we can just do is valid color mem0, mem1, mem2, and then remove all of that. And then here, where's the other one? Is valid color cent_r, cent_g, cent_b. The irony of doing that is what we're going to do next is actually going to undo a slide. piece of that. So here in our setup function, we have all this stuff that is basically reading the color values. So really this isn't a setup thing. This is individual. This is something that should be done in another function. So we'll just take those and we'll get rid of these serial prints for now. I will create a new function here, which can be called read colors. And read colors is just exactly what it says. It's a function that reads the colors. There is a way of shorthanding this that is probably a better and more readable way. So at the moment, what we're doing is saving a value to memory slots 0, 1, and 2 as the whatever the value is that's come in from memory. We're validating those colors based on either the memory values or then this whatever we've defined here as the default setup, which is normal brightness 0, 0. There is a better way of doing this. And it's going to mean we can remove a bunch of these, but it does mean we need to add a default state for the lights. So we've got these normal brightnesses here and everything at the top. What we actually probably want to add in is defining a default red, which we'll do as 255, a default green, 0, and a default blue, again as 0. So we've got these default values we can now refer to, which would mean instead of using normal brightness 0, 0, we'll just use default red, default green, and default blue. Okay, that's one good start, but there's a way of making this even better. And in the end, we want to end up with this mem-r, mem-g, mem-b value set. That's where the end of this thing comes in. So what we're going to do, instead of doing all of this, is say memory value red is equal to, and then we're going to use a single line shorthand, if this, then else that. So if the memory value red is a valid color. So we're going to validate it at this point. So is valid color, but this is a single color, so it's if valid color each. So that's going to say, is this thing true? If so we use a question mark, then memory red is EEPROM read 0. If it's not true, set it to default red. So this is a really easy string. If I do it 3 times, it'll help show what's going on. So memory red, memory green, memory blue, slots 0, 1, ooh, and 2, 0, 1, 2, default red, default green, default blue. So just to reiterate, what this is saying is memory red is validating whether or not this is a thing. So we remove the requirement to have these initial saved memory 0, 1, 2, 3 slots. If it's valid, if it is a valid color, then set it to it. If it's not a valid color, set it to the default. It means we can get rid of all of that and all of that. So read colors just becomes this nice, simple thing. One thing we want to do though is, again, for readability purposes, is these aren't particularly easy to remember. They're just numbers that refer to memory address slots. So what we should do is define memory address slot definitions that are more readable. So let's do memory attributes. And then here we have default colors. So memory attributes are going to be defining, let's call it something that's easy to know what it is, EEPROM red address. And the EEPROM red address And we can do red address, green address, and blue address. Zero, 1, and 2. So instead of just using 0, 1, and 2 for those addresses, as we have done throughout, we can just use these names. So red, green, and blue. I believe there are some rights that we have as well. Well, there must be some rights. So if we just look for our right statements here. So again, all this stuff here. So right to the blue. And I believe I just saw another one there. Read the blue. And then this one should be green. Again, this helps for lots of reasons. Readability is a big one, obviously, but also the fact that we can then come in and if we need to change those address locations for some reason, for example, we've made a mistake and it's done 100,000 writes to that memory address and it's not usable anymore, we can come in and just switch these here and it switches throughout the entire code. We actually aren't using memory 0, 1, and 2 anymore, so they can go away. So it's just memory RGB. We've got our modes, we've got our loops, we've got our states, we've got a state manager, we've got current mode, we've got a settings bit. We're going to come to that in a moment. I'm going to take this NeoPixel color here and I'm just going to put it at the top. Basically, I'm just trying to keep my helper functions up above the code that's going to refer to them. It'll just help me avoid any referencing issues where a function is being created after it's been called. Okay, so we get that. Now we've got read colors here, so it probably makes sense that we're going to have a write colors function as well, instead of just saving write colors within wherever it's used within the code. So we'll have write colors is here. So this does it basically on the validation. It does the write. So we'll just extract that, do write colors. There's going to be a problem with doing this, is that sent R, sent G, and sent B aren't available in this function. We haven't passed them in. So we could do it one of two ways. We could either do sent R, sent G, sent B in this here and pass it into it, or we could actually just utilize the way that we're holding colors throughout the entire application a little bit better. It makes sense for a lot of reasons to do it the second way, and can basically change up the way that we're using stored values, because at the moment we're doing a bunch of different variables to achieve the same thing, which is really there is a set of RGB values being passed around. So really we only really need to ever refer to them once. So we're using memory ones, we're using sent ones, they're all the same. So as part of our constant definitions here at the bottom, let's just start int red value, green value, and blue value. So they start up just as empty integers. We're not going to need these memory values anymore because everything's going to refer to those, other than like in this one, which is doing specific colors that are being passed into it. We're going to, every time we're doing memory stuff that's reading in and out of the memory, we'll use those three values. So when we read the colors, which is the first thing that happens when we I'm saying read and I'm writing read. So when we load the application for the first time, it does this read colors and it sets those 3 RGB values. So they're the ones that now are getting passed back out to the application. So in our send and reads here, so when we're doing our ready request here and it's creating a string, we don't need to repoll this address. We can just use the values. Cuts down on unnecessary requests to the memory. Now this would be able to change. We could just put in red value, green value, blue value here, but this whole thing's about to get scrapped, so it's kind of not worth it. But inherently, most of what we want to achieve with making this better, more readable code is kind of done. There are a couple of things we didn't do previously, which we should have. For example, this should run a commit after you've done a write. It just tells it to store those new things in memory properly. Also in here, this is where we need these values again. Similarly to this commit in the setup, much like we have a Bluetooth begin, we would have an EEPROM.begin, which will run on a low baud rate of 512. So that's just going to start up the EEPROM on the internal memory. So that'll all be good to go. As far as updating readability, reusability, all that kind of stuff in this is now significantly better, significantly easier just to come in and read what is going on because of things like the way we extracted different values. Oh, so here, for example, there you go, there's another one, red value. That probably would have failed if I tried to verify everything, which we'll just do now, just to make sure there's nothing else that I've missed. Ooh. Could not convert is valid color from void to bool. Oh yes, that's my mistake. So these are returning true falses, so they shouldn't be voids. You would do a void if it just received something and did something but didn't return something. Because this is returning something, a true false, it needs to be a bool, not a void. So that all compiles now. So this is it set up for the HM10 using basically better programming standards. Now though, we do need to adjust it from the HM10 to an ESP32. And this is where kind of the biggest part of this is going to happen, because the code that is used for an ESP32 communication is very different. The big crux of what is different is when we use one of these little things, a HM10, it knows what it is and what its function is going to be. It's always just going to be a Bluetooth module. So when you give it power, it goes, hey, I'm a Bluetooth module. Check me out. Here's my name. Here's my connectable information. You may connect to me. That's all it ever does. So when you give it power, it starts doing that. When you're using an ESP32, it has built-in Wi-Fi, it has built-in Bluetooth, it has a bunch of stuff. Until you tell it to turn the Bluetooth on and to be a connectable thing, it doesn't know to do that. So whereas that one, we just gave it power and then said, okay, cool, we're good to go. With the ESP32, we have to set up the server, we have to set up the service on the server, and then we have to set up the characteristic on the service on the server. So the server basically then goes, I'm a thing, you can connect to me. The service goes, oh, I run on this and I just handle a few little bits and bobs and the connections. And then the characteristic is the thing that actually receives the strings and sends things back. It's the actual, the specific communication, like it's almost like a port with the Bluetooth chip. So we have to set all that up. The code that we use to create all this stuff, no one ever just remembers. It's something, it's like one of those things like regex. Everyone just copies and pastes. So let's take a look at this. This is the GitHub for some of the ESP32 BLE Arduino code, the Bluetooth low energy. In here we have lots of stuff, but the ones we want are the examples, and for our instance, server. So these are all different things. Notify is basically sending information out. We're going to be using that. Scan is looking for stuff. Server is what we're using. We're creating a thing that you can connect to and send information to and from. So that's a server. So when we look inside this code, we'll find a bunch of stuff, and really I'm going to try and explain some of this now as we put it into this code, but really a lot of this is just like kind of a boilerplate that you're just going to pick up and just drop into your code. You don't have to understand the complete minutiae of it. But let's get into it. So we are going to need all three of these, the device, the utils, and the server. So we're going to bring them in, and we're going to remove the Bluetooth HM10 that we were currently using, and we're going to include these new ones. The next thing we'll notice is that instead of using service IDs and characteristic IDs that are already defined in the Bluetooth, because if you remember when we did it with the HM10, we used a Bluetooth low energy reader application to go in and find those service and characteristic IDs. We're going to set up our own. So we'll just copy and paste these just here for using them. But like it literally says above it, we've got this UUID generator.net, when we can come in here and create our own UUIDs. So it means that these are nice and unique for us. So we'll just generate two. There we go. These aren't the ones I'm going to be using in my final application. You are not going to be able to hack my car. So we've got our characteristic and our service IDs in here. Great, that's that done. Some of this code will require, and some, not so much. But let's go down to our setup function here. And this Bluetooth.begin currently initializes our Bluetooth. We're not going to be using it like that anymore. Instead, we've got to do most of this. So like I said previously, before we were just turning the Bluetooth on and just saying start. Now we have to set everything up, which is what most of this code does. So what do we need and what don't we need? So this Bluetooth device in it is going to initialize a new Bluetooth device. So it's basically saying, turn on this thing that you've got Bluetooth in you, turn on. What name do you want to use? So I call mine spoiler alert because it's a play on words and it's an alert light in the back of my spoiler. Then these next two blocks here, what they're saying is the server is going to then, use the device, and it's going to create a server. So these are just a lot of different packages that all interact with each other. So like I said, at the top here, we've got device, utils, and server. Device is the thing. So it's now creating a Bluetooth thing on it. We're going to create a server. So then on that device, we're going to create a server. And then we're going to create a service on that server, which uses the service ID that we've just generated above. So this is our service ID. Then we create a characteristic on that service using our characteristic ID, which has two properties. It is readable and it is writable. So we need both of those things in order to be able to pass information to and from. So that means we've set up the device, we've set up the server, we've set up the service, and we've set up the characteristic. And then the next one, service start, kicks everything off. So it starts up the service, but it's currently not saying I'm a thing that can be connected to. It just exists. So that's where these next lines come in, these advertising ones. So if we just take all of those, after we've done our service start, we put our advertising in. What this then does is tell the Bluetooth chip, tell the world that you exist and you've got all these details. Some of these are just like specific for iPhone connection issues. I'm never going to be using an iPhone with this, so I don't need those. I don't also need the scan response. So I just need this little bit. And then that will have basically set up the entire Bluetooth, set up the services, set up the characteristics, set up everything. And it's now turned on and saying, hi, you can connect to me. So we've set up our Bluetooth module and it's now broadcasting and advertising and saying, I'm a server, you can connect to me, here's my details. But it doesn't know how to handle information coming back and forth. And we do that using callbacks. And what callbacks are, for example, a server has a bunch of actions that are already defined and attached to it. So if we go into the source here and look at Bluetooth server, towards the bottom, it'll have the callbacks. And in here, there are callbacks for on connect and on disconnect. So this is handling what happens when something connects to the device and when something disconnects to the device. So those are things we can use within the callbacks. Then, you know, the characteristic has a bunch of callbacks that it can use. The service has a bunch of callbacks that it can use. So there is documentation for this. And, you know, there's some that we'll want to use and some that will not. But let's start by putting in one, just to give you a really good example, is here. After we've created the server, we can do a P server, which is the name of it, set callbacks, and then callbacks are actually a class because they are events attached to the higher level object. So it's a class. So we have to use the new command here. We'll just call it server callbacks. Then above here, we need to set up a class called server callbacks. Now it doesn't look like this because it's an instance of a class. It's not a function. So the way you set this up is a little bit more specific, and you have to refer to it as a public class. And the one that this one is BLE server callbacks. Now, there's no way you're supposed to just know this. This is predominantly in the documentation. So if you were to start going through some of these examples, there will be a bunch of these which will have this stuff in them using them. I can't tell you exactly off the top of my head which ones those would be, but here we go. So my client callback is there, notify callback. So this has callbacks in it that it uses. So some of the documentation and some of the examples will help you out with being able to know how this setup is. But just then we have to define it as public. And then we have the names of our events on there. So on connect, which is a void, and void on disconnect. I'm going to try and just make this as easy to understand as possible, but what's really happening is there are events happening and the Bluetooth is handling stuff on them. So when a disconnect happens, or when a connection happens, or when someone sends a string of code to a characteristic, it handles it and does something. Now it does something within its own, you know, set of code, but we're saying when that thing happens, also do this other thing that we want it to do. So we're attaching our code to an event of a thing that's already occurring. That's basically what we're doing here. We're tapping in to those existing events and adding an extra little bit of code on top. So these on connects and on disconnects have a required thing that we need to pass in, which is going to be BLE server P server. Again, it's in the documentation. Don't worry about it too much. What is the thing you want to worry about is what we want to actually do when this connect and disconnect happens. The irony of setting this up is we don't actually use connect and disconnect in our application right now. We could So let's just give it something to do. We'll set a bool at the top here of device connected is equal to false. So when the application starts, there's no device connected. And then what we can do in here is just do device connected is true. When it connects and when it disconnects, oh, device connected is true. When it disconnects, it's equal to false. We might also just for like our own debugging purposes want to put in here that serial.println of device connected. If nothing else, just having that for showing us in the command line that the device is connected and the device is disconnected is good for debugging purposes. So that's our server callback done. The big bit of this code is done in the characteristic callback. Fortunately, it's pretty simple because really only one thing, one event is ever happening, or one action. We're only ever doing a write event. We never just randomly send out unsolicited data to our phone. Even the setup code is done as a response to a ready request. So we send it the word ready and it responds. So really it's responding to a write. It's not just sending anything out at the beginning. So when we come down to the characteristics here, after we've started the characteristic up, we can do a p characteristic, much like we did before, set callbacks and give it a name of new characteristic callback. I've just realized a mistake I've made is that I've put a little s there. Because these are classes, these need to be have a capital first letter and can't just camel case with a lower. So these are uppercase. So we've got server callbacks and then new characteristic callbacks. Great. So this is going to allow us to attach things to the characteristic events. And it's going to look very similar to this to start with. So it's class characteristic callbacks, public. So being BLE server callbacks, it's funny enough, BLE characteristic callbacks. And again, we have public here. And then, like I said, the only thing that we're actually attaching anything to is an onWrite function. An onWrite takes BLE characteristic. I think that's the last time I need to write the word characteristic. It's one of those things that I'm sure I've probably spelt wrong at least once here. But we need to pass these through this characteristic information because the values that we send back and forth are attached to this characteristic variable here. So we need to have this on here. So where we've got all this code down in here with the settings, so this loop, checking if the Bluetooth is available, not necessary anymore. This here is what we're going to be replacing. So the set settings is gone. And all this code is what's going to come up into the characteristic callbacks. So let's just pop this in here and then look at how we're going to change it. So when we did it in V1, let's get rid of these print lines just to make things a bit easier. We had a Bluetooth command string, which we were then setting to the read string until a new line. This isn't done anymore. We're not going to call it Bluetooth command anymore. Let's just call it value. We'll worry about the type in a second. And the value, like I said, is going to be this P characteristic get value. So whatever is passed into the characteristic is going to set into this value. Now we know that it's going to be a string of some description. It's either going to be the word ready or it's going to be a set of color values. So we're going to set it up as a standard string type. Now we don't need that Bluetooth command. So it's just the word value. Now you would think maybe that'd do it. And it'll be, yeah, probably most of it would be fine. That'd work. Unfortunately, we do need to do some extra checks and stuff in there and just make this a little bit better. And we want to get rid of using this string splitter, because using string splitter is using a unnecessary third-party application when we could just do it in native code. Also, these BT prints and the way it responds doesn't work anymore because we're not using that old Bluetooth print, so that doesn't work. We'll start by swapping that out, because the way it does it now is by setting a new value to the characteristic and then sending that value out with a notify. So its response way is P characteristic set value to whatever the response that we're going to do is. We'll worry about that in a moment. At the moment it's like saved RGB, so let's just use that. And then P characteristic notify. So we set a value to the characteristic here, which is this saved RGB concatenated string, and then we notify. So that would do what we want it to do. Otherwise, down here, we're using string splitter and we're setting out those values and we're writing the code. Again, this would kind of all work. There are probably better ways of doing this though and avoiding string splitter. So let's start with that and then we'll improve this concat as well. One of the problems that we have in C++ is it doesn't like splitting strings unless it really knows the position of the thing that it's splitting it by. Not like in JavaScript, you just say split by commas, and it doesn't care about the distance in between those commas. C++ cares. So what we need to do is find out the position of those commas first before we split it down into the three parts. So we need to find the index or the position in the string of the comma, because we could be sending it 1 byte, then a comma, with like just the number 5, then a comma, or we could be sending it 212 with a comma. So in the first instance, it's index 1, so 0, 1. And then in the second instance, it's index 3, so 2, 1, 2 in the number 212, then the comma. So it's further along. So we just need to find the positions of those commas. So we'll do an integer for comma 1 is going to be value, so the value that we've passed through, the value that we're receiving, dot find a comma. Because this find is only taking this one attribute, it's just going to find the first one. So that's going to find our first comma. Then if we do comma 2, we need to change this to comma 2 plus 1. So this is going to find the first comma and then find the position of basically the second comma. So that's, sorry, that's wrong. That should be comma 1 plus 1. And in fact, these aren't actually finding the commas, they're finding the position of the comma, which is an index. So really we should call this comma index, just again for readability. So this is finding the first comma because it starts at the very start of the string, And then this one is going to find, but it doesn't start searching until the position one character after the last comma that we found. So that's what this second attribute does. It starts to find one step further along. So we've got the positions of those two commas, and we just need to do a quick verification to make sure that everything is within an expected range. So we can say if the comma index for the first one is not equal to -1. So basically, if the first comma is in the string, if it exists, and the comma index 2 is not equal to -1, so the second comma exists. So that basically just confirms that both commas are in the string. And just make sure that it's not outside the end of whatever string that we've put in there. And if comma index 2 is less than value, which is the string that we've sent through, dot length -1, because it's an index value. So the length may be, if the length is 8 characters, then the last position could be 7. So we're just going to make sure that it's all within, kind of like, are the two commas within the string? That's what that line does, basically. So we're going to define 3 new colors that are being passed through: in red, in green, and in blue. Because we've set up the variable type as a standard string, we can do a substring on it, which allows us to look at a small amount of the code. So if we were to do value.substring 0, that'd take everything from the first byte, position 0, for the entire code. If we were to do it from 3, it would go to the third index, which is basically the fourth byte along, and take everything from then. But if we were to take 3.2, it would go to the third indexed position and then take 2 characters, so position 3 and position 4, and that's all it would take. So using that and the fact that we know where our commas are, we can just break apart the whole value into its 3 smaller numbers like this. So value substring, we know it's going to start at the first byte, and then because of the differences between indexes and actual numerical values, we can just say we want to go for wherever the comma index 1 length of string is. So if the comma index, let's say our red value is 55, the comma index is at 2, because 55 is 0, 1, and then 2 is the comma. So 0 and 1 are 5 and 5, comma is 2. So this is saying we'll go for 2 characters long. So start at 0, 5, and go for 2. So 0 and 1, which will give us the 5 and the 5. Similarly, another easy one is going to be the blue, which is just going to start at the comma index 2 and 1 further along. So comma index 2, add 1. So we know the comma position 2 might be at, index 6. We go to there, and then we want to go to the next one and just take that one to the very end of the string. So that's comma index 2 plus 1. In the middle, we want to start 1 space after the first index. So comma index 1, add 1. And then in order to figure out how big it is, we need to do the comma position 2 minus the comma position 1 minus 1. And that'll give us the length. I know it sounds confusing, but trust me, the maths works. So comma index 2 minus comma index 1 minus 1. And that'll give us the length of the middle characters. So there we kind of have it, but not really, because we want these to be ints. And at the moment, these are standard strings. Unfortunately, we can't just change a standard string to an integer. It won't allow it, and C++ will try and kick our ass. But we can do a little bit of a workaround by changing it to a C string, which is completely valid. So we'll do that for all three. So convert them into C strings. And then we can use a toy, A-T-O-I, to convert all of that to an integer, because we can convert C strings to integers. So by doing it like this, like I said, this is fun with typings. So with this little bit of code, we're basically converting that string to that standard string to a C-type string, and then it's reconverting that C-type string into an integer and saving those new integers into these new red, green, blue values. That is by far the most confusing bit of all of this code that we're going to be doing. So if you manage to get through that, the rest of this is going to be a breeze. What we want to do is just validate those colors that we've just done. So we're going to take this valid color checker here. So if valid new red, new green, new blue. So if they are valid colors that have just been sent through, this really should only happen in the instance that the commas and everything are correct. So it's actually a sub loop. Then the global values that we're using to pass everything around, which I called red value, can become new red. Then we can just use these. So if the string format is correct, pull out the numbers, save them as integers. If those integers are valid numbers, using our valid number function that we created here, then update the global values that we're passing around into those no colors. So now immediately at this point, when that red value, green value, blue value is done, when we activate glow mode, those colors will be in there and that'll be set. Now it does also need to update the memory, because the big difference here is initially when we were pressing the glow button, we were extracting the numbers from memory. We're not doing that anymore. We're just using the ones that are being passed around. Really the only ones that are being read from memory is during startup, because that's the only time we really need to access the memory. What we do need to do now is write the colors. So we'll then can do our write colors function, which we had down here. And now none of this string splitter needs to exist. In fact, most of that doesn't need to exist anymore. Oh, I've got so many of these, I'm going to have to do a verification in a minute, make sure this is all okay. But we can write colors, because write colors runs off the global red, green, and blue values. So now, instead of just reading and writing unnecessarily to the memory, we're literally only doing it. We're writing to the memory when things are successful, but we're not rereading it because we don't need to. We're just passing variables and, actually updating the globe based on those variables, as opposed to doing it based on red memory values. The last bit we're going to do is just do a better way of doing this string here, because using this string type, not great. They have a habit of potentially running away with you. So we're going to do two things. We're going to increase how good this check is, this value is ready, and then we're going to do a new way of concatenating that string. So instead of doing just if value is ready, we'll do if value dot compare. So this is going to look at value, and we're going to give it some parameters to compare by. So we're going to start similarly to how we did down here with these indexes. Start at position 0 and go for 5 characters. And then we're going to look for the word ready. And if that is equal to 0, then it's happy, it's valid. So this is basically the reason we're going to do this is sometimes a Bluetooth can get blank characters and things like that at the end of a string. You might get a slash new line or a 0 ASCII character, and it would mean that the length of the string is wrong, or you know, looking to match the term ready, but it's really ready with a slash and some extra information that's hidden at the end of it that you don't know about. With this, we're just taking the value and we're literally just looking at those 5 characters, so it's ignoring anything else that might be there. So it's a better way of checking that that value command is correct. Then we're going to set a thing that we're going to respond with. So response, which can be a character, but we don't want it to be just one character. We know that the maximum length of a thing that we're going to send back would be 3 numbers that are 3 digits each, so 9, plus 2 commas. So the maximum length this can be is 11. So we'll create basically an 11 bytes of character. Then we can use a call function called sprintf. And what this can do is just allow us to use almost like a regex type commands to create a string and replace parts of it with variables. So if we go for response, we're going to be operating on the response, which is a bunch of characters that we just said. And we're going to create a format, which is %d, %d, %d. So the %d is basically just a placeholder for a variable, and we can use as many of those as we want throughout this. We just happen to be using 3 because we're using 3 colors. And then we've got those values, those global color values, so red value, green value, and blue value. And it's going to basically go, okay, so take this response, which we know is an 11 character byte, set it up to this format, and then take red value and swap it in here, green value, swap it in here, blue value, and swap it in here. So we're going to make a maximum, it might not necessarily be 11 characters, but a maximum of 11 character string with these new values inserted in place. And once we have this response string, we need to send that back as a response to ready. We've already seen how to do that, that we did down here with the p characteristic set value. So we can do p characteristic set the value to response, and then simply notify, which will send that back. And there we go, bing bang boom, our entire code is updated for an ESP32. There's one little thing I want to add that we didn't have in before, and it's just another layer of error checking, because at the moment when we use the Bluetooth app and we send a new color, we just assume everything's fine. We don't have any way of it coming back and saying, yeah, that update was fine, or no, that update wasn't fine. So we're just going to do this bit here. So if it is a valid color and we've done the you know, the write to the memory and everything, let's set a value as updated. Otherwise, if it's like not a valid color, let's set the value to failed, and then regardless, send that back. So when we send a new color from the app, it'll respond with either updated or failed. I do need to then update the app to have some kind of check in there to see whether or not that happened, and maybe throw an error state or something on there, but that's not what I'm worrying about with this. So I believe that is everything updated. Oh, we can remove this because we don't use that on the Bluetooth string anymore. So let's just quickly go through it and see what else we can just remove. So we've got our new setup of our Bluetooth stuff, our NeoPixels, our EEPROM. We've got our pins, pixels and the brightness and all that stuff. Now we've got addresses, which we can refer to by a name. We've got defaults that we refer to by name. And we've got this new state management, which we can refer to by name, making things a lot easier. Service IDs and characteristic IDs, and then our initial setup of our modes. And we switch from the word state to mode. We've got our initial red, green, blue values and the fact that our device is connected or not. Then we set up our NeoPixel lights, and then we've got two color validation ones, one that passes it the RGB, and then individual color validators. We can read the colors, which uses the shorthand to validate if the color is correct, and if so, set it to the memory value, and if not, set it to the default value. We've got a write, which writes to these, and I've got a feeling that commit line is going to become valid again because I'm changing from an Arduino Nano to a ESP32 dev module. Similarly, in the setup, it complained at me for doing a EEPROM begin at 512, which I don't think it should have complained at. I think it was just because we were set up for a Nano. We'll see in a second when we click verify and see what I messed up. Then we've got our server callbacks. So these are just listening for that on connect and on disconnect actions and setting the variable to true or false, depending on, you know, what happens. Then we've got our big new characteristic callback. These are the crux of everything now. So we get the value, we compare it to the strings ready with only the first 5 characters, use this new sprintf to create a string instead of using concat, send that response and, you know, send it back. Otherwise, we find the values of the indexes, use those to find the correct substring, convert that to a C-type string, and then convert that to an integer and store those integers, check the integers, and if they're correct, update the colors, the right colors. Right colors here should only happen in the instance that the color validation happens. So that needs to go there. And then reply, updated or failed correctly. Then in our setup, we've just got pin modes, set up the serials, not begin, not. And then we set up our Bluetooth and started advertising with all the various service IDs and characteristic IDs on there. And we've got these new functions for the different modes. So our display mode, which we can just pass it a name. So what we might want to do in setup, at the end of all this setup, after NeoPixel begins, is do a display mode DRL mode and just guarantee that it kicks off into DRL mode properly. And then we just set our kind of, you know, like our color values in here. And we've got our helper function for the setting NeoPixel colors. So all of these just refer to that. And then a loop at the very end, which just has the things that listen for the reads of these various states. Set the mode, basically a state manager, and then, you know, switches the display and switches what is the current mode. All lovely. The only thing I want to do is take this function and put it above display mode, because this refers to a function and I want that function to appear before it's called. So if we verify that, I'm bound to have missed commas or something. We did quite a lot of coding there without checking it along the way. Usually you would do a lot more checks, but let's see what I goofed up. It's okay. It's always semicolons. Semicolon is the bane. I guess there are probably other IDEs that we could be using that would have verified and checked these things along the way and would give me like little red wiggly underlines to show me that there are mistakes. But here you go. But inherently, I think once this is all verified, that's it. So let's just run a compile. I think we've got everything. Let's see if it kicks us off about this EEPROM. I've just, you know, quickly run through it. And I think we've got everything in there. I did forget to put the read colors in. There we go, it's done. I did forget to put the read colors in the setup, so I've just added that. as well. But that inherently is everything. That is the entire thing adapted from the HM10 through to the ESP32 with a load of new kind of like better coding standards. Hopefully you can see why we would do this and why it's worth doing this, especially if we want to then iterate on this, make it a bit more production ready, or things like adding new states. It's going to be a lot easier to manage everything. I know this was probably quite a coding intense video and not what you expect if you're coming to me generally for car content, but yeah, this was something that we're going to be using in a car. So if you are looking at creating your own brake reverse multifunction cool Bluetooth controllable light in your car, I will make this code available. It's in the description down below, so if you want to check that out and have a play with the code yourself, you're very free to do so. If you do make something cool with it, make sure you send it to me, tag me on here or on Instagram on Valentine Autos on everything. And yeah, I want to really see what cool projects you're able to do with this or the code surrounding it. If you've got any questions or comments, or you think I could have solved some of those problems in a more efficient way, then definitely let me know. I'm always up for hearing ways of approaching solutions that you think might be a good way of doing it. Obviously, if you like this kind of content, you know where the subscribe button is, and if you find this useful, be sure to give it a little thumbs up. Whatever you do with the rest of the day, have a wicked one, and I will see you in the next video. Take it easy, peeps. Bye-bye.